Best behavior. Yeah, there's the guy. Make it real. Make it your own little project.
I already did.
Oh,
Here's a model of the Earth and Earth-Moon I say Earth-Moon because there is more than one moon in this star system. The size of the Earth and Earth-Moon are to scale. The distance is not to scale. There's more space between the Earth and Moon of Earth in reality. I have the Earth and Earth-Moon closer together to fit onto a television screen, 352 by 240 dots, also called pixels. You can see that the Earth is tilted to the star humans call the Sun. The Sun I call the Earth star, or the star Earth rotates, would be seen above and to the left of the Earth. What is interesting are all the different rotations happening. The Earth and Earth-Moon rotate the star, the Earth-Moon rotates the Earth and the Earth-Moon both rotate on their own axis. That is 3 separate rotations. The Earth and Earth-Moon are tilted at 23 degrees from the plane that most of the planets and other matter rotate in. This plane is different from the plane of the Milky Way galaxy. The planets and most moons, including the Earth-Moon, orbit in a counterclockwise direction when looking down at the North Pole of the planet Earth. Some of the moons in this star system orbit in the opposite direction, rotating a planet clockwise. Phoebe of Saturn and Triton of Neptune are 2 examples. This makes me think that the speed and tilt of each planet and moon may depend on the combined effects of individual pieces of matter that collided to form each planet and moon. When I first made this model, I made more than one error. Since I have never seen a model of the Earth and the Earth-Moon, for example, a film of the Earth and Earth-Moon taken from a camera orbiting the star outside the Earth orbit, perhaps in between Earth and Mars, a film that shows one moon rotation in 1 to 5 minutes. So from books and data on the internet, I learned that the moon rotates the Earth in 27 days, while the planet Earth makes a complete rotation in only 24 hours. So for the first time I realized that the Earth is spinning faster than the moon, with the Earth-Moon rotating slower than the planet Earth. I never realized that every part of the Earth can see the moon of Earth at some time in the 24-hour rotation. Before I thought that the moon rotated at the same speed as the Earth and only one part of the planet could see the Earth-Moon at different times. An interesting thing I've read, first described by the son of Charles Darwin, George Darwin, is that the Earth is slowing, and eventually, with no change in movement by life, the Earth-Moon will continue to move away from the planet Earth. At that time, only one part of the Earth will ever see the Earth-Moon. I think that humans will grow other species on the Earth-Moon in my lifetime, with a maximum of 30,000 more days. Of course, after my death, my body will continue to decay here in the star system. Life will probably grow cities and thousands of buildings on the moon of Earth. Eventually, the life living on the moon, perhaps with their own moon money, will want a different cycle besides 14 days or 328 hours of light and 14 days of dark, and may want to use nuclear fission or fusion or some new process to turn the moon of Earth to a 24-hour day-night cycle more like planet Earth. Perhaps the life living on the Earth-Moon will want to be free of the planet Earth and life of Earth sometime, and will become a planet by moving to an orbit circling the star in between Earth and Mars. What an exciting time that will be for humans in the rest of life, a time when humans actually care for science, learning, and truth, with the religions of life a bad memory. This is a model of the 25 closest star systems to the Earth star. Most English-speaking humans on planet Earth call the Earth star the Sun. I use the words Earth star or star the Earth rotates because the Sun is a star, and one of the most interesting products of the star is the life that seems to be growing on one of the planets that English-speaking humans have labeled Earth. Life may be growing on the planets that orbit every star in the Milky Way and every galaxy in the universe. I like to say Earth star, and sometimes main star, instead of Sun. This view is looking down on the North Pole of Earth at these 25 star systems as you rotate in a counterclockwise direction. You may see that the Centauri star system, made of 3 stars, a triple star system, is closest to the star Earth orbits. Most humans never realize that another yellow star is only 4 light-years away from here. Think of what planets and pieces of matter must be orbiting these 3 stars, and how interesting the movements of matter must be between more than one star. Some matter may orbit 2 stars, or orbit 1 star for thousands of orbits, or years, and then change to orbit the other star for another 1,000 years. So the Centauri system seems the obvious choice for humans and life to explore first. I think that humans will send a vehicle that uses nuclear explosions to move a camera and radio transmitter at accelerations that no human could ever live in to the Centauri star system. The ship would have to turn around 180 degrees halfway in between the Earth star and the stars of Centauri and start decelerating until stop when Centauri is reached. Humans feel an acceleration of 10 meters per second squared on planet Earth. People call that 1g. 3 Gs, or 3 times the acceleration of Earth, would probably be not comfortable for humans and would cause problems to most human bodies. Of course, machines would not have problems at 3 or 4 Gs, even as much as 10 or 20 Gs, or 20 times the acceleration of planet Earth, 200 meters per second. At an acceleration of 200 meters per second squared, 20 times the acceleration humans feel on the surface of planet Earth, a vehicle could reach the stars of Centauri in 30 Earth years. The images moving at the speed of photons would take 4 Earth years to get here from there. What would you and I see? There have to be planets, and at a minimum some kind of matter, orbiting the stars of Centauri. There may even be planets with some kind of life growing on the surface. When I first started to make this map and model these stars, I had to learn the system used by humans in astronomy, or star mapping, for thousands of years. This system uses right ascension and declination to measure the location of all the stars. The stars are mapped as if humans were looking out at the inside of a sphere. So right ascension is a horizontal measure and declination is a vertical measure. For some reason, right ascension is measured in hours, minutes, and seconds instead of degrees. So these values go from 0 to 23 hours, 59 minutes, and 59 seconds. Declination is measured in degrees and minutes, ranging from 90 degrees, that is looking in the direction of the North Pole, to minus 90 degrees, looking in the direction of the South Pole. In this view, right ascension is easier to see than in a side view where declination would be easier to see. For example, the 12th closest star system to the Earth star, the double stars Groombridge A and B, is at 0 hours, 18 minutes, right ascension. The 5th farthest star system, L725-8AB, another double star system, is at 1 hour, 39 minutes. Number 9 in distance is a beautiful orange single star system called Epsilon Eridani, and this star system is at 3 hours, 32 minutes. Continuing in a counterclockwise direction, you can easily see the stars Sirius and Procyon. Sirius is the largest of all the stars in this map and would probably be the easiest star to see for life looking at this part of the Orion arm of the Milky Way galaxy for the first time. Sirius is the bright blue star you can see in the constellation called Canis Major. This group of stars is below and to the left of the easily seen group of stars called Orion, visible when the Earth is in the winter part of orbit. To see Orion during a cloudless winter night, look for the 3 stars on a line forming the belt of Orion. Sirius is at 6 hours, 45 minutes right ascension. The Sirius star system has 2 stars. A white dwarf star orbits the main blue star and is called Sirius B. Next you can see the 4th farthest star, Lalande 21185, a red star system at 11 hours and 3 minutes. Centauri is at 14 hours and 39 minutes and is really the only star that has been found in this direction, right ascension. Number 14, named 61 Cygni, is at 21 hours, 6 minutes. Finally, star system 8, Ross 248, and star system 18, Lacaille 9352, are 2 red dwarf stars located at 23 hours, right ascension. The order of the closest stars, according to most humans, has changed in this decade and may change again because red dwarf stars are dimmer than larger stars and not easy to see. In addition, the distance of each star is measured by parallax. Parallax is the amount of space a star appears to move when seen from 2 different locations, like both sides of the Earth's star. The more a star seems to move relative to objects more distant, the more close the star. This is the same thing that you can see when you look at an object and switch from one eye open to the other eye. You can see that the apparent location of the object seems to change compared to more distant objects. You can do this until you are tired of closing and opening one eye at a time, as I am. A ship made by humans of the European Space Agency called Hipparcos, named after one of the first humans to make a map of stars, measured the distance of more than 100,000 stars by parallax, and this data may change the order of closest stars to the star the Earth rotates. According to the data I have, Star System 1, the Centauri stars, are 4.3 light-years from here. Star 2, Barnard star, is 6 light-years. Number 3, Wolf 359, 7.8 light-years. Number 4, Lalande 21185, 8.2 photon Earth years. L726-8 AB and Sirius, numbers 5 and 6, are both 8.6 light-years from here. Star 7, Ross 154, is 9.6 light-years. Star 8, Ross 248, is 10.4 light-years. Epsilon Eridani, Star 9, is 10.7 light-years. Star Systems 13 and 14, Epsilon Indi and 61 Cygni, are both 11.3 light-years from Earth. Tau Cetus, the single yellow star, number 16, and Procyon, number 17, are 11.4 photon years. Captain Star and Kruger 60, numbers 24 and 25, are both 13 light-years from me. So you can see that this star map has a radius of 13 light-years from the star Earth rotates. In this view, you are on the same horizontal plane as the star Earth rotates. A human viewing this model is rotating in a counterclockwise direction, circling the 25 closest star systems with the Earth star in the center 13 light-years away. In this view, you can see declination. Stars like number 25, Kruger, are at 57 degrees declination, above the Earth star. Star system number 14, 61 Cygni, is at 38 degrees. The fourth closest star system, Lalande 21185, is at 35 degrees. Procyon AB, star system 17, is at 7 degrees declination. Sirius is at minus 16 degrees. Negative declination values are below the plane of the star. Lacal 9352 is at minus 35 degrees. Captain Star is at minus 45 degrees. Epsilon Indi is at minus 56 degrees. I think the declination is based on the axis the Earth spins on, the equator. You can see that the Centauri system at minus 60 degrees declination, number 1, is below the south pole of the Earth and seems to move the least, since this star system is almost directly below the Earth star and is the closest star system to the star the Earth orbits. This map shows the 25 closest stars to the Earth star. The space between the stars is not to scale so that I can show you all the stars on one screen. The sizes of the stars are to scale except for the red and white dwarf stars. These stars are actually smaller and could not be seen at this scale. In terms of space between the stars, 14 dots, or pixels, equals 1 light-year. The speed of a photon is 300 million meters in 1 second. The space a photon moves in 1 Earth year, called 1 light-year, equals 9e15 meters. That's 9 exponential 15 meters. A 9 with 15 zeros after. 9 quadrillion meters, or 9 trillion thousand meters. So Centauri at 4 light-years away is 9 times 4, or 36 quadrillion meters away from here. To compare, the planet Pluto is 5.47 light-hours from the main star, or 5.9 trillion meters, 1/60,000th, or 0.0006 of 1 light-year. 1 light, or photon hour, is like 1 trillion meters. In making this model, I had to change right ascension, declination, and distance in light-years to 3-dimensional triordinates. Most humans use the word coordinate. I use triordinate because I'm using 3 values for each star, not 2. A system using 2 values in degree form, like right ascension and declination, and 1 radius value, like distance in light-years, is usually called a polar coordinate system. I wanted to map these stars in what is called a rectangular coordinate system. Most humans would call a rectangular system a Euclid, Descartes, or Newton-based system after 3 humans that use this kind of location system. This system uses 3 values for each point in space. 1 value for left-right, another for up-down, and the last value for forward-back, with the value 0, 0, 0 as the center of this type of modeling system. To change from polar to rectangular with right ascension and declination, I used the equation x equals light-years times the sine of declination times the sine of right ascension y equals minus light years times cosine declination, and z equals minus light years times sine declination times cosine right ascension. These equations are for a negative y-axis, since this is what my drawing program uses. Once I had the three-dimensional rectangular values, triordinates, I could calculate the space between all the stars with the equation distance equals the square root of x squared plus y squared plus z squared. When I did this, I learned that Tau Cetus, number 16, and L725-32, number 21, are only 0.93 light-years apart, less than 1 light-year apart. The closest star to the star Earth rotates is more than 4 light-years. So I learned that other stars may be closer together, even less than 1 light-year apart. The same is true for Procyon, number 17, and BD plus 5, 1668, number 22, only 0.94 of a light-year apart. Ross 248, star system number 8, and Groombridge 34AB, star system number 12, are only 2.05 light-years apart. Tau Cetus, star system 16, and L726-8AB, star system 5, are only 2.85 light-years apart. Humans exploring Tau Cetus, the only other yellow single star system like the Earth star in this 13 light-year radius, will probably explore L726-8AB, number 5, 2 light-years away, and L725-32, number 21, 1 light-year away. Even the smaller red dwarf stars may have life growing on orbiting matter. Making the spheres that represent stars included making spheres of triangles, adding a light source, and then changing the three-dimensional triordinates to two-dimensional coordinates. I am not sure what objects in the universe the word energy represent, and am now thinking of interpreting the universe in words that apply to matter only. For the star temperatures, I used the OBAFGKM color lettering system. This system uses one of these letters and a number to define what color each star is. For example, Sirius is a hotter blue A1 star. The Earth star and Centauri A are both yellow G2 stars. Tau Cetus is a yellow G8 smaller star. 61 Cygni A and B are orange K5 and K7 stars. Barnard star and Wolf 359 are cooler red stars with M4 and M6 spectral type. An interesting note is that the Kelvin temperature scale is an absolute temperature scale. At 0 degrees Kelvin, no matter moves. Humans call this temperature absolute zero. Hydrogen and helium gases are liquid and solid under 10 degrees Kelvin. The Kelvin scale is the same as the Celsius scale, only 273 degrees higher. So 0 degrees Celsius is 273 degrees Kelvin. Think of how life may shape the universe. Life may want to use matter to change the matter to some other form. Hydrogen may be used to fuse to helium, the same process that stars use to make photons of light. Life may want to collect extra gas from the galaxy and feed stars to keep a star burning for more time. Life may take matter from stars that may go supernova. How to take matter from a star is a good question, since the temperature of most stars would melt iron at some distance. Maybe life of the Milky Way will move each star to equal distances and turn the shape of the Milky Way galaxy into a sphere of yellow stars. Maybe the matter of the universe will try to stop the expansion of the universe. Maybe that time has passed and life has missed any chance of stopping the expansion of the space and matter in the universe. Maybe all universes are started with exactly enough matter to stop any expansion and collapse each universe to make a new universe from the momentum of the collapsed universe. When I started looking at all the languages humans have used and are using on planet Earth, I noticed that each language uses most of the same sounds. Humans, myself included, have started to make computer programs that use a set of these base sounds to make words and allow a computer or machine to talk. There may also be robots that use an airbag, much like a lung, to make sounds and talk. One thing I realized when looking at the English alphabet after looking at other alphabets is that there are some sounds that have no letter. So I started making new letters for the sounds that have no letter. For example, the A in cat. I removed the letters C, Q, and X. Since the letter C should be replaced with K or S, the sound Q represent are already defined by the K and W sounds, and X is usually sounded as the letter K or Z. In this new alphabet I made, each letter is defined by one and only one sound. So for example, the letter G will always sound as the G in good, and the letter J will always sound the J sound, as in the word just. This will make reproducing the sounds of this time easier for future humans. Pronouncing words of the past is sometimes difficult since a symbol could represent 2 or 3 sounds. You must have at some time in your life pronounced some word different from the popular pronunciation and were immediately imprisoned and or tortured in a psychiatric hospital. Spelling words has also been a guessing game, since letters like A and O can have 2 or 3 different sounds. Plus there are letters that are sometimes never pronounced, silent letters. What stupid humans started this tradition? In this alphabet I made, each letter is called the sound that the letter equals. For example, I replaced the sound for the letter humans call C with the ch sound. So in this system, the letter C would be called the letter ch. At this time, to make learning to use this alphabet as simple as possible, I only made one set of capital letters. I tried to make letters that humans can draw in one stroke for speed. One idea I thought of is that the number of spaces between each word can be the amount of time delay between words.
What is exciting to me is that each letter has a real origin.
What are the first sounds that humans made letters for? What letters are the oldest letters? What letter was the first letter? When were some of the more new letters and symbols made? And how? The oldest letter E ever recorded has to be at least as old as the Greek alphabet, since the letter epsilon is included in the Greek alphabet. The sound E is at least as old as the pyramids and the Egyptian hieroglyph. The same is true for the sound O. At this time, I recognize 36 distinct sounds used in human language, 13 new letters for sounds that had no label, and 23 sounds already defined by a letter. There must be more distinct sounds used by humans on planet Earth that I have no identified, so I think that this alphabet will grow. This is the alphabet I am defining. A, B, D, E, F, G, H, I, J, K, L, M, N, O, P, R, S, T, U, V, W, Y, Z, A, Ch, E, H, I, J, A, R, Sh, Th, Th, In this screen, I have also included the 10 decimal numbers and 5 other symbols to remind everybody that there are other symbols of value with definite origin times on planet Earth. Here are messages in different languages using this alphabet for each language. G, D, J, A, O, M, S, D, O, R, B, A, O. Sh, E, E, O, D, W, T, B, A, N, K,